Excellent. Hello, this is Physics Lab 4 Oscillation by Alexander Lavrenyuk. So, as you can see, this is a table of contents and the introduction. This lab was aimed on learning how to predict movement and energy of an object set in motion while hanging on a spring in closed grip. One of the main principles we used was Newton's second law. It states that the acceleration of the object depends on its mass and net force acting on it, and that the change of momentum is the same as the force acting on the object. Then we also use the principle called energy principle, which states that the energy is not created and not destroyed. And the equations about the equality in energy at all times in the locked system, and also the potential energy of the spring, which we'll be using later. So introduction, and here are the graphs and images of the results. Now the initial conditions. We had a ball of mass nearly 0.4 kilograms in the given position, and it's hung by the spring with a stiffness 6.83 newtons per meter, while the spring is compressed by the given length. The system obviously is Earth, the ball, the spring, and air, although we're not counting air in the model, so we can forget about it. Now the experiment was filmed on video, and I tracked it using tracker, put the coordinate system, and calibrated the lens to be the lens of the spring. Otherwise, it would be illogical. Then computational model. So on the left, you can see just the code for plotting all the graphs. And on the right, the start of the initial conditions about mass, position, and velocity. Velocity is obviously zero because the man is still holding the ball. And then it's the import of data from the local file and timing. I set up the time to the time in the tracker and delta to the delta time in the tracker, which would make perfect sense to compare the both models. So then we have the constants, which we counted. Also, how did we get the spring constant? We got it from the period. And how did we get the period? We just took how I did it. I took 3 periods by x-axis and just divided them by 3 and found average period. And from that found the spring constant. The relaxed length of the spring. And then we find out the L vector, which is like pretty obvious. We find the energies using the formulas for each of the energy and the total energy. Then we, through the cycle, do pretty much the same, but updating velocity and position every time so that we have changes in energy. And then we plot these changes in energy. And on the right, you can see the formulas in velocity and position we use to update the velocity and position for us to see the dynamic graphs. So then the result. On the left, we see the graph of change in energy and also an image of how the ball was moving in the model. On the right, you can see X and Y position over time with model and experiment combined both. So what does it mean? And conclusion questions. So first, let's start with what could be the sources of problems and issues. Well, firstly, the source of errors is that experiment was not precise, and we did not count air resistance, we did not count other forces, we did not count temperature change, we did not count the perspective of the lens filming it, and we did not count the fact that tracker is a little bit imprecise, especially when you're tracking it by hand. Now, for our model system, is the energy principle satisfied? Yes, it is, because the energy principle says that energy cannot be created or destroyed, and we see that the delta energy is 0 in this bound system. So what we also have, we have that data obtained in tracker, we calculate 2 separate estimates of oscillation periods. So the first one we find through the x-axis, and the another one we find through the y-axis. Why they are different? I guess because of the precision in tracking of both axes. But as y was having a bigger difference, the period was smaller. Pretty much that's it, but I guess it's just the error in precision of tracking the point in both axes to make it the same point, because it's just tracked by hand. And that's pretty much it. Thank you all for your attention.